The research that we're doing for the FAA is all about understanding how aircraft that use integrated propulsion and control function. Specifically, these types of aircraft are those being developed for a future where we're going to have air taxis flying all around. How we're doing that is a mixture of both developing theoretical math models and building two 80-pound quad heli test beds. We've been studying how different ways of controlling the individual rotors on a multi-copter system like you see here will affect or impact how the entire vehicle itself is controlled and the handling qualities of the vehicle. At the same time, we're looking at methods to predict what the forces and moments are required of the vehicle to fly a given trajectory. So in the end, we can compare and see, can it actually fly that trajectory? And we hope that this one day can become part of a tool set that test pilots can use prior to flying these very novel types of vehicles. So hopefully that will increase safety and give the test pilots more information about what they're about to go do. So many of these companies that are developing these vehicles, they utilize a specific type of rotor control that's called RPM control. So in that case, the rotor's pitch is fixed, and they use the change in the RPM to change the thrust. They're very simple. That's one of their advantages. One of the drawbacks is when you scale them up to a passenger-sized vehicle, the inertia of the rotor grows, which can impact the handling qualities. Another way that's seen less frequently is to govern or keep the RPM of the rotor constant and then change the pitch of the blades. This is slightly more complicated, but it does give you the advantage of having faster response time. Another method that we're studying here at the Eagle Flight Research Center is using full helicopter control on the rotors of the multi-rotor system. So not only to get collective pitch, like I just mentioned, but we also use cyclic pitch, where the pitch of the blades is changed as it goes around. And this can asymmetrically load the disc with lift, and thereby causing it to tilt slightly and also putting a control moment. It gives you a lot more advantages. So not only do we have one control, now we have pitch control as well as cyclic pitch control, which gives us more controls than we need. So part of our research is understanding how to blend these controls together to optimize the way that the aircraft flies. It also gives us the ability to add redundancy to the system. So in the case of a failure, we can still control the aircraft. One of the major milestones that we hit was actually showing that we could control the aircraft stationary, no pitch, roll, or yaw, with one of the rotors completely inoperative. And to us, this was a big breakthrough. Additional funding in a phase 3 from the FAA will allow us to really sort of hit the final challenge, which is bridging the gap between component level design and how that affects the handling qualities of the vehicle to how well the vehicle can fly its mission in terms of it being certified to carry passengers.